Thank you, Janine. Good morning, everyone. First of all, I'd like to thank Janine for inviting me. I love to speak about 5G. It's something I do quite often. And also, on behalf of Analog Devices, the host sponsor, I'd like to welcome everyone to EDI-Con, welcome you to Boston. For those of you who are from out of town, please get out and enjoy. The weather's great. Boston's a great place to spend some time. So we're going to talk about 5G. So 5G, has anybody in the room not heard the word 5G? Okay, that's a good start. So 5G, 5 years, how do we get there? And a lot of it relies on the people in our industry, the people in this room. I'm going to start with one word, and it's connectivity. So what is wireless all about? Wireless is about connectivity. And I'm sure most people have smartphones. Smartphones are getting more and more capable. But two of the most terrifying words in modern society is no service, right? You look at your phone, no service. You need this connectivity to tweet, to friend, to share, to Uber, to Google, to Siri. If you don't have connectivity, the phone really doesn't do that much for you, right? It becomes a camera, it becomes a music player. So what we've shown really in the industry is as connectivity is improved, and you saw the chart that Scott put up of the data growth. A lot of data growth, it really is, it's fueled by better connectivity. As connectivity gets better, we generate more data. And it's sort of a self-propelling industry in that regard. And our challenge really, at least in my mind, as an industry, our challenge is to get connectivity to the point where you don't think about it. That you don't worry about being connected, you're just connected. So the title 5G in 5 years really came from, when Janine sent me an email inviting me, I had just read this Ericsson Mobility Report. Anyone who hasn't read, they're very good. They come out a few times a year. And one of the data points was in 2022, which happens to be 5 years from now, we'll have 500 million 5G subscribers. And there are other forecasts of 1 billion, 1.5 billion, and different time frames. And so I wouldn't really focus on the numbers. But this is only 5 years away. And in order to accomplish this type of subscription rate, really we need to have our networks and our devices in 2020, or maybe before that. So this is what I'll talk a little bit about 5G today and how we can all help this happen. So we'll start with of course, the obvious question is, what is 5G? So obviously 5G is what comes after 4G, but 5G is much more profound and a much larger scope than just that. And if we look at the three, it's generally divided into three areas. So we have at the top enhanced mobile broadband, which is more of what we have now. We have on the two bottom circles, we have massive machine connectivity, which is largely defined or called IoT. And then we have the mission critical, so ultra reliable, low latency services. Today, I'll talk more about the enhanced mobile broadband than anything else, because really that's what's coming the fastest. The mission critical, however, I see personally, in my opinion, as probably the area where you may see the most disruption going forward in wireless. Having these very reliable, low latency connections available will enable new business models that we haven't even thought of yet. That's my own personal opinion. But so we see these three areas. There are these key performance indicators set out by the ITU probably 2 years ago now. And, you know, there are some 8 or 10 of them. And we would not expect to accomplish all of those at once, right? So you see they're sort of clustered around, whereas for ultra broadband, you know, we're looking at very high peak data rate, very high data density. Whereas we look at the massive machine connectivity, it's all about very dense sensor networks. So there's diverse applications, and one of the key features of 5G, which differentiates it from any other previous generation, is flexibility. It's the ability to enable new use cases, new markets that we do not currently address with the mobile industry. So how does it impact us? So we'll just come down a level now, and you think about specifically, I'm going to talk about base stations. That's where I spend most of my time. I'm not really going to dwell on devices personally today. But if we look at the 5G NR, so 5G NR is the common name for the standard that's coming through the 3GPP. And what is, these are just a few key takeaways from what's percolating out of 3GPP. Really, so 5G is going to be deployed in new spectrum. We hear a lot about the C-band now, opening up bands globally, and we hear about millimeter wave. So it's higher frequency, wide bandwidth. Those are two key properties of 5G NR. It will be very light for the base station, maybe not quite this for the handset, but for the base station, the waveform is not significantly different than LTE. Slightly different, so it is, but not very much. And beamforming. So beamforming is a large proponent of 5G, one of the foundational techniques of 5G. We do see it rolling out now, and people will call it 4. something G, but it will be one of the foundations of 5G. And then if you look at my colored chart there, we see that 5G is not limited to millimeter wave or massive MIMO, although those are what we see as what we call the new technologies that are being introduced in 5G. But 5G will also be rolled out in macro base stations on current assets. It will be rolled out in small cells, and if you do see this in the news, that small cells really are gaining momentum, and small cells will be a big part of 5G. So I'll talk about the two items identified, so massive MIMO and millimeter wave, really the two key areas for radio designers going forward. So what is massive MIMO? Also known as full dimensional MIMO, and again, it depends on, it's a generational thing, how you address it. But I think overall, it seems to be referred to generally as massive MIMO. So what is massive MIMO? Well, the architecture, we see my hand-drawn version of an antenna panel. It does use, in general, digital beamforming, whereby behind every antenna, there's a full radio chain. Generally, high radio counts, 64 transmitters, 64 receivers, is sort of the common number, or more or less, depending on what kind of configuration you're looking at. And you may actually have more than one antenna on a radio, maybe there's 2 or maybe 3 antennas on a radio chain to get a little more gain. But I say, in general, we would say it's a 64 transmitter, 64 receiver system. And the technology, as we will lift the lid here in a minute and look a little deeper, what you will see is that the technology is not significantly different than what was being deployed in current base stations. Although, as we go on, we'll see there are lots of room for improvements and innovations in these systems. What are the benefits? Well, the benefit of this system is a step change in spectral efficiency. And if you're a mobile operator, you only have a few things you can do to increase your capacity. You can buy more spectrum, you can add more base stations, or you can improve your spectral efficiency. And really massive MIMO, these systems, even with the current specifications, we're seeing 3 to 5 times improvement in spectral efficiency and throughput in the field trials. And then, in the research areas, we see enormous improvements possible in spectral efficiency. So what is inside one of these? Oh, actually, I'm going to talk about challenges first. So what are the challenges? We say the benefits are great, but also the challenges are, because we're going from, say, a 4 transmit, 4 receive system to a 64R system. It doesn't come for free, right? So the challenge is, size. These things can only be so big because of wind loading, et cetera, and even installation. So you are limited by size, you're limited by weight, and of course then size and weight are somewhat dictated by power consumption and cost, of course. You also, if you think about the number of radios inside one of these panels, the interface, the amount of data running around the inside of that panel is enormous. And then, of course, getting that data on and off of that panel is also a big challenge, and we will see some changes to the front haul protocols as we go forward into 5G. Now we'll see what's inside. So what's inside? Conceptually, as a block diagram, what you see here is there are a number of radios. So you've got a number of RF chains. Looks a lot like a current RF chain. Or you can actually imagine it as a number of small cell radios paralleled up. All and you have clusters of them because your digital front end can only support so many interfaces and so many channels. So it's typically, say, 8 feeding an ASIC or an FPGA. You have a calibration channel. Typically, there'd be 1 calibration channel for the entire array. And then we have our antenna processing unit, which does the actual beamforming, analyzes the channel state, does all that matrix inversion, and then generates the beams going out, and then your front haul interface. So that's what's inside one of these systems. Now, so we'll look about innovation a lot. There are, of course, always ways for innovation. I remember some 20 years ago when I was a young engineer well, not that young, but I remember one of our executives at the company I was at the time saying, "There's nothing left to be done in RF, it's all done." Right? That's a long time ago, and there's been a lot done in the last 20 years. So there's always room for innovation, and I'll start on the top left, and imagine 64 radios, you have 64 filters. You can't possibly use a traditional base station duplexer in these systems or a traditional system, right? If you're looking at air cavities filters, they're fairly large, and it's an interesting space because if you look at the industry, we've focused on high power systems for the last decade or more, really. For filters and power amplifiers, these have been, pushing up the power, 20 watts, 40 watts, 60 watts more. So, the filters are designed in a base station to handle a lot of power. And here you're in this area of, 1 watt, 2 watts, up to 5 watts of power. So it's a different requirement. But really, the emphasis here is on size and cost, right? Because if you have 64 filters or more, really, 128 actually, if you have 1 on the transmit, 1 on the receive, it can add a lot of weight. So we see there's work being done in filter design, filter materials. We see the saws and the BAWs are becoming more capable for power handling. So we do see, it being approached from different ends, really to optimize the filter for the application. And then, of course, there's algorithms. There's things like self-interference algorithms. And, we do a lot of work on algorithms ourselves at EDI. Then we move down to the PA, of course, same with the PA. The PAs in that 3 to 5 watts, Doherty's are now coming online. We've done a lot of work on DPD, and actually there's a presentation tomorrow afternoon, I think it's the last session of the day, on what we've done for low power DPD, whereby we've optimized the DPD for the PA size. Because you really, if you have a 5-watt PA, you really can't be burning a watt of power for your DPD. You need to get something in the milliwatts. And then, of course, there's still lots of room for innovation in the actual small signal radio. And here, I actually show this divide. We have the CMOS for the most part, and a lot of this was driven by EDI and some of our peers. We've really brought CMOS to bear on the radio. And, my associate Frank Kearney presented this morning on 0IF. So we've utilized 0IF because 0IF is the most conducive architecture to this type of integration. So, and there'll be a few other presentations on this as well, on these CMOS transceivers. But if you then think about it at a high level, if this entire block is CMOS, how do you optimize it? How do you partition it? One of the things we've shown is that just by bringing the DPD across the barrier from the one chip to another chip, you reduce the number of SerDes lanes by half. In these panels, there's something like 200 of these SerDes channels. So if you can take away 100, that's huge. I mean, it results in some, depending on what type of GSD link you're using, it can save you 10 to 20 watts of power just by doing that. So I say there's lots of room for innovation. I'm just touching on this at a high level. Now we'll move on to millimeter wave. Millimeter wave, we say loosely, it's operating in the greater than 10 gigahertz area. Again, very high antenna counts, but it's a different type of beamforming, and we'll talk a little bit about hybrid beamforming. Really, the challenge here is utilizing the large amount of spectrum. The reason we're looking at millimeter wave is because you can get access to enormous amounts of spectrum. And that enables you to get very high throughput without a high spectral efficiency. But then again, if you can push up spectral efficiency, you can get a higher throughput. Challenges here. If we look at some of the challenges, there's a lot of work being done in the industry on, the channel models. There's still a lot of work being done. We're faced with fading, blockage. Blockage is a real problem at these frequencies. And so there is a fair amount of characterization being done on various materials on the attenuation. And then there's beam acquisition. You don't want to consume too much of your time acquiring and tracking the beams. And then from a radio perspective, again, as I mentioned earlier, very wide bandwidth on the order of, say, gigahertz nominally of bandwidth. And then, of course, power consumption and cost. So just to talk a little bit about this hybrid beamforming, what is it? It's essentially, if you look at what I've drawn here, you have, say, data streams. You have a number of data streams with A to D converters, D to A converters, and then you do your up and down conversion. And then you split it into a number of RF paths, and you form your beam. So you're using analog beamforming. Why we call it hybrid is because you can add this level of MIMO, so to speak, whereby you have multiple data streams. So you have some digital pre-coding and some analog pre-coding, or say beamforming. So what are the challenges here? You'll notice the word efficient. I use the word efficient a lot. There are systems in the field. There's a lot of field trials ongoing. We were able to produce radios as an industry. I'm sure that a lot of people in the room may be working on these. And the technology actually is advancing as we move from, say, a 3.5 based architecture to silicon, to CMOS. But still, efficiency, I think we have a long way to go. And I would say, really, we're just getting going here. If you look at what we've done in sub-6 gigahertz, I believe that can all be done here over time. So we look at, the PAs, The PAs, so if you're looking at a silicon type implementation, at back off, and this is one of the problems of these systems, if you're at a 10 dB back off, your efficiency is not very good if you're using a Class AB type amplifier. So, there is work being done, I believe, in bringing Doherty to these frequencies. It's not simple, I don't think. And then, then we add predistortion. So we push up the efficiency, and then adding a predistortor is also a challenge in these systems because you have multiple paths. So there are specific challenges around that. And then even if you look at the architecture, I would say, which is what we normally do, we start with architecture, and architecture ultimately gets paired with technology, and you optimize your system. So I would say, this is the hybrid beamforming architecture. Will this stand the test of time? Probably not. This works today. It's the most efficient today based on given technology. But if we can migrate to a digital architecture, I believe the digital architecture will win out over time. But again, there are challenges really in getting the power down in these radios, right? These A to D converters today, if we're trying to sample a gigahertz, we're running at, say, a 3 gigasample per second ADC. These things consume power. So we have to look at, how do we create a more efficient architecture? My personal belief is we move to a zero IF architecture. That's where I think we'll make great improvements in the radio architecture. So we have testing. I think there's a lot of test people in the room, and I'm not going to dwell on that, but there is a lot of work being done on over-the-air testing. I think we're making good progress there. And then this idea of calibration, there are papers that would say you don't need to calibrate, which would be wonderful. And then there's other people looking at different calibration techniques. So calibration is an active area of research. So I'm just going to close with a prediction, more of a mission statement, I think, for us than a forecast. And as I said earlier, part of our goal as a community is to bring connectivity to the point where you don't even think about it, right? So 20 years from now, it's an arbitrary number, but I think given our trajectory, I think this is possible, that in 20 years, connectivity, you would just be connected. And I can't even begin to predict what the device will be, what it would look like. By then, maybe we'll have grown antennas. I don't know, right? But if you think about it, 20 years from now, I hope to not be saying, how is your 7G connection, right? Or are you on Wi-Fi? Or how do I connect this thing? No, in 20 years from now, the technology and the networks will have evolved to the point where it'll be just like air, right? It won't be free, I'm sure, but it will be something that you don't think about. And I think that really, for us as a community, really that's our mission in connectivity. And I'll close there. I'm here for the next 2 days. Come around. I might be at the booth. Come around and see us. We have some great demos there at the booth. And it's been a pleasure to speak to you today. Thank you.